This is the 16th video in a series that I'm making to support a course in elementary number theory. And in this video, we're going to talk about the notion of the order of an integer modulo n, as well as the notion of a primitive root, and then prove some companion results related to those ideas. Okay, so let's look at our first definition. So we'll suppose that we have a natural number n and an integer a, and these two numbers are co-prime. So in other words, the GCD of a with n is equal to 1. Then we define the smallest natural number m such that a to the m is congruent to 1 mod n as the order of a mod n. So let's also use the following notation. So m is equal to ord underscore n a. So we read that as the order of a mod n. So let's recall from Euler's theorem, sometimes called Euler's generalization of Fermat's little theorem, we know that a to the phi of n is congruent to 1 mod n. So that really tells us that the largest this m could be is equal to phi of n. In other words, Euler's totient function evaluated at n. And we're going to get to that kind of thing a little bit later in this video. Okay, so let's do a big example dump first before we start proving results. So let's notice that 5 to the 1, well, that's congruent to 5, which is not congruent to 1 mod 12. That tells us the order of 5 is not 1. But if we take 5 squared, we get 25, which is congruent to 1 mod 12. So that means 2 is the smallest exponent, so that when you raise 5 to that power, you get 1. That means the order of 5 mod 12 is 2. Then we can do the same kind of thing, mod 9, with the number 4. So 4 to the 1, that's equal to 4, which is not 1 mod 9. 4 to the 2 is 16. Well, 16 is 7, which is not 1 mod 9. And then 4 cubed is equal to 64, but that's 1 more than 63, so that is 1 mod 9. So that means 3 is the smallest exponent that will give us 1 mod 9 when we put it in the exponent of 4. So in other words, the order of 4 mod 9 is 3. Then here's a similar example working mod 5 with the number 2. So 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, which is 3 mod 5, 2 to the 4 is 1 mod 5. So that means 4 is our smallest number. So in other words, the order of 2 mod 5 is 4. Notice something special is happening over here, because by Fermat's little theorem, we in fact know that a to the 4 is congruent to 1 mod 5, and that's going to be true for all a that are not divisible by 5. And notice we've achieved this largest possible order with the number 2. So that's actually going to be something that we properly define later as a primitive root. That means 2 is a primitive root modulo 5. Okay, so now that we've done this example dump, let's start with a pretty simple proposition. Now we're ready to look at our first general proposition involving the notion of order. So let's introduce some notation. We'll say that the order of a mod n is equal to m. So we've got the setup so all of these things make sense over here from the definition. Then we have an if and only if statement. A to the power k is congruent to 1 mod n if and only if m divides k. In other words, this k is a multiple of m. Notice that immediately gives us the following thing, which I have in this orange box. The order of a mod n divides phi of n. Well, how do we see that? We just replace this m with the order of a mod n, and then recall that Euler's theorem says that a to the phi of n is always congruent to 1 mod n. So if we can prove this slightly more general statement, then we've got this orange box for free. This orange box is maybe the most important thing that we take away from this proposition. Okay, so let's look at this proof. Let's go with the forward direction first. So in other words, we want to suppose that a to the k is congruent to 1 mod n. And then as it goes with a lot of these things, we'll use the division algorithm. So let's use the division algorithm with k and m. And so that means we can write our number k as m times q plus r. So we've divided k by m and kept the remainder. So here our remainder goes between 0 and m, not including m or including m minus 1, depending on how you want to write that inequality. That's how I'll write it here. Okay, so now next what we want to do is notice that we can take a to the r power, and notice that that's the same thing as 1 times a to the r power, which is congruent to a to the m all to the q times a to the r power. And this is occurring mod n. And why is that? That's because a to the m is congruent to 1 mod n because it's the order. But now we can use exponent rules here and see that this is all equal to a to the mq plus r. That's occurring modulo n. But now notice that mq plus r is exactly k. So we have that this is equal to a to the k mod n. But let's recall that our assumption was a to the k was congruent to 1 mod n. So we have this is 1 mod n. So what have we done? We found an exponent here, namely this exponent r, so that when we raise a to the r, we get 1 mod n. But this r is strictly less than m minus 1. But then by the minimality condition of the order, notice the order is the smallest m such that a to the m is congruent to 1 mod n. But really the smallest m, which is a natural number. Well, notice all of the possible values of r are natural numbers except for 0. So all of this tells us that the only possibility there is for r is 0. But if r is equal to 0, then that means we can scrub it out of this right here. And we see that the condition that we are left with is exactly the divisibility condition m divides q. Okay, so that finishes this direction of the proof. So now let's look at the other direction. Okay, we finished the forward direction of the proof. Now we're ready to look at the reverse direction, which is actually quite a bit shorter. So let's suppose that we have this divisibility condition, m divides k. But what does that tell us? That means that k equals m times x for some integer x. And now we're essentially good to go. Notice that a to the k will be equal to a to the m to the x. But then since m is the order, we know that's congruent to 1 to the x mod n, but 1 to the x will be 1. So this is all congruent to 1 mod n. That's exactly what we needed to show this reverse direction. Okay, so that finishes this proof. Now we're ready to look at an application of this notion of the order of an integer as well as this proposition. Okay, so let's get that example on the board. Okay, so like I said, now we're going to look at a nice application of the notions from the beginning of this video. And this is also going to build off of a sequence of numbers that we looked at in class. And I also have like a main channel, i.e. a non-course video related to these numbers as well. So let's recall that the nth Fermat number, which we will denote by f sub n, is the number 2 to the 2 to the n plus 1. So what we will show in this example is that all prime factors of this nth Fermat number are of the form x times 2 to the n plus 1 plus 1, where that x is coming from the natural numbers. Okay, so let's see how this goes. So let's first suppose that p divides our Fermat number. So in other words, we have a prime factor. Well, notice the notion of being a factor and being divisible by something are really the same notion. Okay, but that tells us that f sub n is congruent to 0 modulo p. Well, that's just another kind of definition of divisibility. But that tells us that 2 to the 2 to the n is congruent to -1 modulo p. That's just like using this definition of f sub n and moving the 1 over. Okay, but now what we'll do is take this congruence here and square it. So let's square both sides of this congruence. So let's see what that'll give us. That'll give us 2 to the 2n plus 1 is congruent to 1 modulo p. Now, an important thing that I want to point out here is that this squaring is actually a little bit trickier than it seems like it should be because of these nested radicals. So if you're confused by this step from here to here, just make sure to write this pink squaring as multiplying this thing by itself and then carefully use exponent rules. You will use the fact that 2 to the n plus 2 to the n is 2 to the n plus 1. But now using a result that's really in parallel to what we just saw in the previous proposition, that tells us that 2 to the n plus 1 divides phi of p. Okay, but let's recall that phi of p is exactly equal to p minus 1. So if you're worried about this step, let's leave it as a little bit of a warm-up exercise. And that is if a to the m is congruent to 1 mod n, then m divides phi of n. Notice here we're not using the fact that m is the order. It could also be a multiple of the order. But now if 2 to the n plus 1 divides p minus 1, that tells us that p minus 1 equals x times 2 to the n plus 1 for some number x. But now we can just move some things around and see that we immediately have p is equal to x times 2 to the n plus 1 plus 1, which is exactly the form of our prime factor that we wanted to get out at the end. Okay, so now that we've gotten this started, let's now look at a different definition, the definition of a primitive root mod n. Okay, so now that we've looked at the notion of the order of an integer mod n, we're going to look at the notion of a primitive root mod n. So A is called a primitive root mod n if the order of A mod n is phi of n. So in other words, it is the largest possible order. Remember, in a previous proposition, we showed that the order must always divide phi of n. Okay, so that brings us to a really big question. And that question is, when is there a primitive root? So in other words, which natural numbers allow for primitive roots in the first place? Is it all natural numbers or maybe just some of the natural numbers? Well, let's look at a couple of examples. We can't solve that big question today, but we can get started on that. But like I said, before we get started on that, let's look at some simple examples so we get an idea for how this is going. So if n equals 10, then phi of 10 is equal to 4. And that's easy to check by a formula that we proved in a previous video. So we're looking for something of order 4. Well, let's notice if we take 3 to the 1, 3 to the 2, and 3 to the 3, we do not get 1. So that means the order of 3 is not equal to 1, 2, or 3. But 3 to the 4 is equal to 1, which means the order of 3 is equal to 4, but that's phi of 10. So that tells us that 3 is a primitive root mod 10. Now we could have done this a little bit more efficiently. Notice we know that the order of an integer modulo n always divides phi of n. So we really just needed to look at the divisors of 4. We only had to check that 3 squared and 3 to the first were not equal to 1 mod 10. We didn't have to look at this 3 cubed. Okay, so let's look at a non-example. So let's say n is 12, phi of 12 is 4. Again, you can check that using a strategy that we had previously. Now let's notice 5 squared, that's 25, which is 1 mod 12. 7 squared is 49, which is 1 mod 12. And 11 squared is 121, which is also 1 mod 12. And then very simply 1 to the first power is 1 mod 12. Well, that tells us that everything mod 12 has either order 1, if you're the number 1, or order 2. but that means nothing has order 4 and there is no primitive root modulo 12. So there we've got an example. 10 allows for a primitive root, 12 does not. Okay, so from here, we'll actually prove that all primes have primitive roots, but we need a bit of a preparatory lemma in order to do that. So let's maybe get that preparatory lemma on the board. Okay, so like I said, we need a preparatory lemma to prove the punchline of this video. And this preparatory lemma says that if you sum over all of the divisors of n, phi of those divisors, you get n itself. So I think there's a name for this sum. Maybe post in the comments if you know that. And so I worked out an example just so we can get a feel for what's going on here. So if we sum over all divisors of 15 of phi evaluated at those divisors, well, the divisors of 15 are 1, 3, 5, and 15. So we've got phi of 1 plus phi of 3 plus phi of 5 plus phi of 15. So that's 1 plus 2 plus 4 plus 8. But it's easy to check that that's equal to 15, which is exactly what we want it to be equal to for this thing to maybe check what we're going to prove in this lemma. Okay, so how are we going to do this proof? I'm going to do it on induction on the number of prime factors of n. So we're not inducting on n, we're inducting on the number of prime factors of n. So let's start with our base case. So our base case would be n has a single prime factor. But if n has a single prime factor, that means it's a power of a prime. So that means we can write n as p to the r. Now let's do our calculation. So we've got the sum over all divisors of n of phi of those divisors. Well, if n is a power of a prime, then it's easy to write down the divisors. So d divides n if and only if d is equal to p to the s, with s is between 0 and r. So if it's equal to 0, that's the divisor 1. If it's equal to r, that's the divisor, which is the whole thing. Okay, but that means we can rewrite this as a sum as j goes from 0 all the way up to r of phi of p to the j. And now something a little funny is happening at the j equals 0 term. We can't use the standard formula for the Euler phi function evaluated at a multiple or of a power of a prime there. So we're going to take that out. So we've got this is 1 plus our sum as j goes from 1 up to r of phi of p to the j. Really, this 1 is phi of 1, but phi of 1 is 1. But now we can use our formula for the Euler phi function evaluated at a power of a prime and see that this is equal to p to the j minus p to the j minus 1. Now we're going to go ahead and split that into two sums. So we've got that this is 1 plus our sum as j goes from 1 up to r of p to the j, and then minus our sum as j goes from 1 up to r of p to the j minus 1. Now we're going to re-index this second sum. So let's re-index this by replacing j with j plus 1. So that means this p to the j minus 1 will change to p to the j. And then our index will start at 0 and end at r minus 1. But now let's notice that the 0th term will cancel out with this number 1 here. So let's maybe take this 0, cancel it out, and then we can cancel this number 1 here. Well, that's because p to the 0 is equal to 1. And then furthermore, we have exactly the same terms in this second term, in the second sum as we do this first sum, except this first sum has a p to the r term. So that means we get a bunch of telescoping action. So in the end, we're left with p to the r. That's because the j equals 1 term here will cancel the j equals 1 term here all the way up to the j equals r minus 1 term, which will be canceled over here. But look, p to the r is equal to n. And now if you look at what we've got, our extreme left and right hand side, that's exactly what we wanted to prove for our base case. Okay, so now let's get rid of this. We'll make an induction hypothesis and move on from there. Okay, we just got done with our base case. Now we're ready to look at our induction hypothesis and prove the induction step. So let's suppose that our statement holds for all natural numbers with k prime factors. And then we want to consider a new number, which I'll call n, which is a little bit sloppy because I have an n right here. But this n is playing the role of all natural numbers with k prime factors. And this new n is maybe distinct. And it has k plus 1 prime factors. So we're going to write this as n equals p1 to the r1 all the way up to pk to the rk times p to the k plus 1 r k plus 1. Okay, so it's got k plus 1 prime factors. Then I'm going to smash all of these together into a new number, which I will call m. So in fact, we can write n as m times p sub k plus 1 to the r sub k plus 1. And now m has exactly k prime factors, which means if we can somehow create a place to use it, we can use this formula on m. Okay, so let's just point that out over here. So if we take the sum over all divisors of m of phi of d, we get exactly m. So that's by our induction hypothesis. Okay, so now we want to start taking the sum over all of the divisors of n of phi of d. And then we can notice that divisors of d are exactly the divisors of m multiplied by a certain power of p sub k plus 1. So I can start by writing this as the sum over all divisors of n that are not divisible by p sub k plus 1. So we can write this as p sub k plus 1 does not divide d. Well, so let's notice that this means that in fact the d divides m because it does not contain a factor of the prime which does not divide m. And then we're going to build this up a little bit at a time, adding in power of p sub k plus 1 one at a time. So the next will be this sum over the divisors of n where p sub k plus 1 divides into d, but no larger power of pk plus 1 divides into d. So I'll note that with this double divisibility sign. And then we'll work that all the way up to the sum over the divisors of n where the largest power of pk plus 1 divides into d. In other words, pk plus 1 to the rk plus 1. Okay, well, let's notice what this means. This means that d over pk plus 1 is a divisor of m. Right? Because if we divide out the factor of pk plus 1, we have something that divides m. And way up over here, this means that d divided by pk plus 1 to the rk plus 1 divides m. So in fact, we're really summing over divisors of m that have just been boosted a little bit by certain powers of p sub k plus 1. So we can write that as follows. This is going to be the sum over all of the divisors of m of phi of d. So that would be like this first bit. And then this second bit will be the sum over all of the divisors of m of phi of pk plus 1 times d. So that would be like this. Notice that we have divisor of m times pk plus 1. And then we're going to take that all the way up to our highest power of pk plus 1. So it's going to be the sum over all of the divisors of m of phi evaluated at pk plus 1 to the rk plus 1 times d. Okay, so now before we move on to the next board, I want to notice that this pk plus 1 is relatively prime to d. And that's because pk plus 1 is relatively prime to m by our construction up here, and d is a divisor of m. And so by the multiplicativity of our phi function, we can take this and write it as phi pk plus 1 times phi d. And then similarly right here, we can take this as phi pk plus 1 to the rk plus 1 times phi d. Okay, so now let's keep that in mind and bring that up to maybe this stage right here, and we can finish this proof off. Okay, so we finished the last board with this line, and now I want to do some factoring. So notice that this object right here, which I'm boxing in orange, does not depend on our summation index, so we can bring it out of the sum. And all of the similar terms in these other summations are also not part of the summation index, so I can bring those out of the sum as well. But that leaves us with a bunch of copies of the same sum. Namely, we've got the sum over the divisors of m of phi of those divisors. So that means that we have something that looks like this. 1 plus phi pk plus 1 all the way up to phi pk plus 1 to the rk plus 1. That's what we factored out. And then the sum over all the divisors of m of phi evaluated at those divisors. But now let's notice that this thing that I'm boxing in blue is exactly our base case setup, because we've only got one power happening there. So that means all of these add up to pk plus 1 to the rk plus 1. And then we can apply our induction hypothesis to this. So I'll just write induction hypothesis applied to that will give us m. But now if we multiply m by this power of p sub k plus 1, we get n. And that finishes the proof of this lemma with induction. Okay, so now we're going to get rid of this, and we will indeed show that every prime number has a primitive root. Okay, now we're ready to prove the main result of this video, and that is that there is a primitive root mod p for every prime p. So we're actually going to prove something a little bit stronger, and that's because it's natural to prove this stronger statement, and it'll be useful for some stuff we do down the line. And that is if d divides p minus 1. Remember, p minus 1 is phi of p. So if we've got a primitive root, it has to be of order p minus 1. So anyway, let's start over. If d divides p minus 1, then there are phi of d numbers of order d. So that tells us we achieve the order of every divisor of p minus 1. That includes p minus 1 itself. Well, what does that tell us? That tells us that there are exactly phi of p minus 1 elements of order p minus 1. In other words, there are phi of p minus 1 primitive roots mod p. Okay, so now that we've got that taken care of, let's look at the proof of this. So let's start by supposing that we have a divisor of p minus 1, we'll call it d, and then we'll consider the following set, which I will call a sub d. This is going to be all of the integers between 1 and p minus 1. So there are p minus 1 such integers such that the order of these integers is equal to d. So it's the collection of all integers of order d. Okay, so now I'm going to prove the following claim to get us off the ground, and that is if a of d is not equal to the empty set, a priori it could be equal to the empty set. Maybe we do not achieve an order of a certain divisor of p minus 1. Maybe we don't achieve a primitive root in the first place. So we don't know that this is non-empty at the moment. Okay, but let's suppose it is non-empty. Then the number of elements in this set must be phi of d. Okay, so that's what we're going to start with. And we're going to do that by proving two competing inequalities. So let's notice that if A is in A sub D, then that tells us that we know A to the M is in A sub D, and that's going to be true for all M between 1 and D, where the GCD of M with D is equal to 1. Well, this is a standard kind of thing that you could prove with the division algorithm, much like one of the propositions from previously in the video. So you would start talking about the order of this thing A to the M. You would assume that it is not equal to D. Then you would do something with the division algorithm and the remainder to show that you've got some sort of power of A which is smaller than D, and that would be a problem. Okay, but let's notice that that gives us a bunch of new elements that are in A of D. How many new ones of them? Well, we've got exactly the number of things that are relatively prime to D, but that's defined by phi of D. So in other words, we've got the number of elements in A sub D is bigger than or equal to phi of D. Again, because if we've got something in there, we can create at least that many more of them. Okay, so now we're going to argue that we actually have an inequality going in the other direction as well. Okay, and we can do that as follows. So let's notice that the A in AD are solutions to a certain polynomial equation. And that polynomial equation, or congruence I should say, is f of x is congruent to a to the d minus 1 modulo p. Okay, but then let's notice that they are not solutions to a congruence g of x, which is congruent to x to the, I'll say, m minus 1, congruent to 0 mod p, where m divides d. Because if they were solutions to this congruence, then their order would be smaller than d. I should point out here that m is not equal to d. So again, we want their order to be exactly d, which means they satisfy this type of equation, but not this type of equation. But now we can just add up the number of elements that possibly satisfy this one, but not this one. Okay, so there are at most d solutions to this, and then to a collection of polynomial equations like this, there are at most m solutions for each of those, where m are the divisors of d. So we've got d minus the number of divisors of d, but that gives us the number of things that are relatively prime to d. But that is exactly phi of d, by the definition of phi of d. So that tells us that we have the inequality in the other direction. So that means the size of a of d is less than or equal to phi of d. But now putting these two inequalities together, we see that we have proved this claim. Okay, so now that we've taken care of that, let's maybe clean up the board a little bit and we'll move on to the next step. Okay, so let's see where we are so far. We constructed these sets A sub d, and we showed that if they are non-empty, they have phi of d elements. But that means they are either empty, i.e. have 0 elements, or have phi of d elements. We want to show that this is an impossibility. Okay, so how can we do that? Well, let's suppose otherwise. So that means we're working by way of contradiction. We're saying that it is possible to have an empty set of one of these. So in other words, let's suppose that d prime divides p minus 1 and the number of elements that are of order d prime is 0. But now next, we know that every number from 1 to p minus 1 is in one of the a sub d. So that's by the definition of a sub d. All of these numbers have an order mod p minus 1. So that means they've got to be inside of one of those. Okay, nice. But that tells us that the set containing 1 up to p minus 1 is actually equal to the disjoint union over all divisors of p minus 1 of a sub d. That actually is going to set up our contradiction. So that means that p minus 1 is equal to the sum over all the divisors of p minus 1 of the size of a sub d. But that's going to be equal to the sum over all the divisors of p minus 1 that are not equal to this d prime of the size of a sub d. Why is that? Well, that's because the size of a sub d prime is equal to 0, so we don't really need to include it. But now that's going to be less than or equal to the sum over all divisors of p minus 1 that are not equal to d prime of phi of d. Okay, well, that's because all the rest of these are potentially of size phi of d. Some of them could be a 0, but they're all 0 or phi of d. That means that's why we've got that inequality. But now that is strictly less than what we get if we sum over all the divisors of p minus 1 of phi of d. Because now we're summing over that d prime as well. But then our preparatory lemma told us that this was equal to p minus 1. So let's see what we've just done. We've shown that p minus 1 is strictly less than itself. But that's a clear contradiction. So what did we contradict? We contradicted this possibility for a sub d prime to be empty. So that means that is not a possibility, which means the size of the number of elements of order d is always phi of d. So that includes the size of the number of elements of order p minus 1. That's going to be phi of p minus 1. In other words, there's always a primitive root mod p. In fact, there are phi of p minus 1 primitive roots mod p. Okay, so now that we've gotten this main result taken care of, let's look at some warm-up problems you guys can do based off of this. Okay, so let's look at the following warm-up exercises, which will get you ready to do some harder problems involving this stuff. So let's find the order mod 10 of 7 and the order mod 25 of 9. Then next, find all primitive roots mod 11, 13, and 17. Then finally, show that there are no primitive roots mod 8 or mod 15. Okay, that's a good place to stop.